Three things we can do to shift an equilibrium. What are they? No. What types of stresses? There we go. Temperature, concentration. I'm too lazy to write concentration, so I'm just going to put square brackets. And pressure, and only pressure affects. And pressure only affected, or gases are only affected by pressure. Solids and liquids, pressure has no effect on them. Okay. I forgot the U in temperature. There we go. Okay, so solids and liquids. Can you change the concentration? No, you cannot. So the concentrations of solids and liquids. And the reason, okay, look, this has a caveat, but really, when you're talking about concentration, it's volume per, or it's moles per liter or something per volume, right? And when you're talking about solids and liquids, when you say those words, you're really talking about the density of them. All right. Now, you can change the density if you heat things up a lot and put them under pressure and stuff, but they are such small changes, we assume, for the purposes of our chemistry class, that there is no change. Okay? So for us, we are not changing the density of solids and liquids. Okay? Now, if I write NaClAq, what does AQ mean? Aqueous. It's dissolved in water. If I write NaClL, that's liquid sodium chloride. You've melted it. Okay? So it's a pure substance. All right? This is dissolved in water. This is a pure substance. This concentration doesn't change. You can change this concentration by adding more salt to the water. Okay? Okay. Temperature also has no effect on the concentrations of solids or liquids. Okay. What does the catalyst do? Oh, hang on. I want to highlight something because I'm probably going to put it on a test. The concentrations of liquids and solids do not change in equilibrium shifts, but the amounts may change. Okay? So what does that mean? If we cool down this system, which way does the equilibrium go? This one. If I cool down that system, which way does it go? Left. It's going to shift left, right? Because I'm taking energy out of the system. So we'll shift left. The amount of sodium chloride will increase. Right? If you're going this way, you're producing more of this. Which means, but if you think about it, this is salt dissolved in water. If you heat up water, you go this way and you dissolve more of it, yes? If you cool down water, what happens? The salt falls out of solution and sits on the bottom. So you're producing more of this. Concentration is the same, but you've increased the amount of it, okay? So just be careful about amount and concentration. What do catalysts do? They lower activation energy, which, do they affect the equilibrium? No, they just determine how fast you get to equilibrium. Okay, they speed up the reaction. So they do not affect the position. They only affect how fast you get there. All right, so Now, how do you use this stuff in industry? Here's one example. Making ammonia, Haber process. German chemist, won Nobel Prize for making ammonia. Making ammonia is very important because it leads to nitrates, which are used in explosives and fertilizer and all this kind of stuff. Okay. Nitrogen is quite abundant, but nitrogen is unreactive. Does anybody know why nitrogen is unreactive? Because it's a triple bond. If you remember your Lewis diagrams from chemistry 11, nitrogen is a triple bond. It does not want to break those bonds. It's hard to do. But which way does enthalpy favor in this reaction? It favors the products. Problem is the activation energy is super high. Okay? So, what would you normally think? If the activation energy is high, you would want to jack up the temperature. What's the problem if you jack up the temperature of this? If you increase the temperature, because this is an exothermic reaction, it's going to push back this way. Right? So increasing the temperature alone isn't going to work. So what else do you do? What else can you do that you know how to do? Sorry? Increase the volume? If you increase the volume, that's decreasing the pressure. That's going to go to the side with more gas molecules. Which side has more gas molecules? Yeah, so do we want to do that? I want to make this. So you're going to increase the pressure. So some reactions are done under high pressure because it'll drive it this way. All right? So to shift this equilibrium, you can increase the pressure. And what else would you want to do? Would you want to do this reaction under high temperatures or lower temperatures? So you decrease the temperature a bit too. But we know that decreasing the temperature lowers the reaction rate. So everything's a balance, right, in industry. But if you can decrease the temperature, essentially you're pulling the energy out, that drives the reaction this way. If you increase the pressure, it also drives the reaction that way. Okay? So you can use equilibrium shifts to increase your yield of production. Okay? And it's a balance. It's a balance of how much increase in pressure and at what temperature to actually get the reaction to go at a decent rate to justify costs and whatnot. Okay? Okay. Now this relates to what we did in the lab on Friday. So we've talked about pulling things out of solution. All right? You don't go in and like pull chemicals out of solution physically. You have to do it chemically. All right? And you did part of this on Friday. So if we have calcium hydroxide, throw it in water, forms calcium ions and 2 hydroxide ions. If I want to pull this reaction this way, okay, I have to remove one of these. Okay, because if I can pull one of these out of solution, you pull the reaction this way, right? Now, on Friday, people were asking me, because you had to decide if you're going to add an acid or a base, all right? So when you see an OH, all right, that's a hydroxyl group. You want to do a neutralization reaction because that's essentially a base, right? If you take an acid, you know what? I'll write it the way they wrote it in the reaction, in the lab. They wrote H3O plus. We do a whole unit on acids and bases. We do 2 units of them actually. The general form of an acid is H3O plus. It's water with an extra proton on it. Okay, so this is the acid. When it reacts with a hydroxyl group, what do you produce? 2 water molecules. and liquid. Okay? Right? This H joins that, and you get 2 water molecules. Okay? It's a neutralization reaction. So if you see a reaction that has OH minus on one side, and I say, how can you remove this? All right? You would say, and we're going to do one at the bottom, you would say you add an acid to react with this, which forms water, which essentially pulls that away out of solution, and the reaction will shift to the right. Okay, we'll do a practice one in a sec. The other thing is if you have 2 ions, ammonium and chlorine, all right? And then do you have your data booklets with you? Open your data booklets, please, to, remember this chart from Chemistry 11? Solubility chart? So we have 2 ions. We have ammonium and we have chlorine. So if you look on that chart, ammonium is right here. Is there anything that will precipitate ammonium? No. So you have to, that is ammonium. So you have to ignore that. Okay? So then you look at the chlorine. Chlorine is right here. What precipitates chlorine? Silver, lead, and copper wire. Okay? So if you add any of those, you will form a precipitate. So, and this is what you did in the lab. I'll bring up the lab in a sec here. If we add silver ions, they react with the chlorine. They form silver chloride, which is a solid. That solid falls out of solution. You did that with, I think it was iron. Yeah, or something like that. And you formed that white color cloudy thing, and then it went clear. That's because you were pulling it out of solution. I have your lab here. I should just pull it up. And nitrate. It was the ammonium. What was it? No, here it is. You add the silver nitrate to it. The silver reacted with the thiocyanate. All right, and you got a white precipitate. Do you remember this? All right, so you got a. Go away. There you go. You got a white precipitate, and it went clear. Did the solution go clear? Like not the white part, but the liquid, the pure liquid. It should have gone clear once it all sort of settled down. Clearish. I'm just gonna look at the people that are nodding at me right now and just go with them. Oh. So it went clear because as you remove this, right? This gets pulled out of solution. I guess it would be pale yellow too. It shifts back from deep red. So we precipitated out this, okay, through this reaction right here. Forms a solid on the bottom. Because you did that, this reaction shifted back here and formed more of the pale yellow in the colorless solution. So it should have cleared from a deep red color anyway. Okay, is that what happened? 2 people are nodding. 3 people are nodding at me. Okay. So now I can ask you a question like this. Give me 3 ways you can shift this equilibrium. Right? To the right. We have no idea about temperature. So we have no delta H information. So what's one way I can shift it to the right? Oh, okay, yep. Add an acid. So add H3O plus, which is an acid. which will decrease the concentration of OH minus, therefore shift right. Okay, that makes sense so far? Right, we want to get rid of this so we can pull the reaction this way. What else can we do? Would increasing the pressure or decreasing the pressure have any effect on this system? No, because there's no gases. So that's off the table. What else can you do to shift it right? What's one of the easiest things you can do to push the equilibrium to the right? Yeah, add stuff over here. So add chromate, CrO4. So add CrO4 negative 2. Equal, I'll just say shifts right. What else? Sorry? That's a pure substance though, right? That's looking at, you want concentrations. Those concentrations aren't going to change. That would dilute the system. You say decrease it? No, that's the right answer. I was just confirming. I wasn't like challenging you. Yes, if you decrease the concentration of this, you will pull it to the right. Now, you have the, is that on your table? No, it's not on your table. So let's say decrease the concentration of Cr2O7 to negative by adding an ion to precipitate it. Therefore, reaction shifts right. There's one other thing you could do. We've already sort of talked about it. If you look at OH minus and you look at the data table or in your data booklet, where's OH minus? Where is it? All right. OH minus with the nothing precipitates with the alkalis. They don't do anything. They're boring. Same with nitrates. That's why we use them. That's if you notice in what we were using, we use like iron nitrate and stuff like that. Those are all spectator ions. That's why we use them. They don't do anything. Hydroxyl group, alkalis, H plus, ammonium, and strontium. It's soluble. Everything else, it is not soluble. Now everything else is a relative term. But so if I added, say, silver or calcium or barium or lead, what's going to happen to this? It's going to form a precipitate and fall down. So it doesn't always have to be an acid with that, with hydroxyl group. You can precipitate it out sometimes. So let's say, wrong one. For precipitate OH minus by adding, I don't know, what do you want to add? Silver, lead, whatever you want. Lead hydroxide, and then your buddy back there can sniff it. Whoever that guy is in grade 11. By adding lead. Because it would be which is a solid. All right. Okay. You can now answer the questions. I think, is that it? Yeah, you can now answer the questions. Lab activity is due tomorrow, which most